You can use different parameter types and user-defined functions to describe instance parameters. Here at the top right is an example of static constants. You enter this value in the object properties form itself, and here at the top left is an example of design variables where the length and width of the MOSFET are defined by the variables that you see here. So before running a simulation, you can set the design variables. Remember that all quantities that are assigned the same variable name will get the same value. Let's look at this iPar parameter that is used here to define the width of this transistor. Note that it uses the parameter name L of the same MOSFET in its attribute. It is a scale function and it returns the value of a component parameter of the local cell. So in essence, the width is defined as a function of the length. As the length changes, the width value will get updated and be used in simulations. You can use basic parameters such as variables, constants, and dependent variables to create advanced mathematical expressions for parametrization. Here is an example on the slide. P-par refers to parent parameter. You can use the P-par function to reference values from the parent instance of a component. The component can be anywhere in the schematic hierarchy. Any top-level parameter defined using P-par is passed down to relative instances. The Netlist shows the P-par definitions as sub-circuit parameters. Here you see an example where the function is used to describe the parameters LP, WP, LN and WN for this PMOS and NMOS. These parameters are created when you use the automatic symbol generator to generate a symbol for the inverter. Now you can instantiate this parameterized cell in your schematic and can pass same or different parameter values. Before you proceed with netlisting, you need to ensure that the schematic is laid out correctly, connectivity is honored and meets the schematic rules check. You need to click on the check and save button or choose check and save from the file menu for this. Schematic checking is a critical step in the design process. Either check a single cell view or descend through the hierarchy to check all the cell views in your design. To elaborate a bit more on what schematic checking accomplishes, it updates connectivity. When connectivity is established, wires and pins in the design entry window become associated with logical connections called nets. Then it also does the schematic rules checks. This process checks the schematic with a set of rules, and you can access the rules from the schematic rules checks setup form. These checks could include logical checks, physical checks and name checks. Apart from this, it also does the cross view checks. This option checks the pin consistency between different views of the cell. Note that pin names and directions must match between the cell views. Let's see how you can enable your schematic rules check. You can choose to run the schematic rules check using the schematic check options form accessible from the options menu. You can enable the run schematic rules check option, which enables the schematic rule checker that performs checks based on options set in the schematic rules checks setup form. Or you can directly choose check rules setup to open the schematic rules checks setup form. The form that you see on the screen has options enabled for connectivity and cross view checks, and you can list the views to cross check in the provided fields. Schematic rule checks can be set up in the schematic rules checks setup form. You can access this form from the check menu. Using this form, you can enable or disable any or all of the schematic checking features. Different types of rules are displayed under different tabs associated with the checks. You can choose to ignore, display a warning, or show an error if rules are violated during schematic creation. This slide explains a bit more about what you saw on the previous slide. There are 3 levels for each check: ignored, warning, or error. Take some time to read what these levels of checks are for. The checks are done for the areas mentioned on the slide, and you saw them as tabs on the snapshot on the previous slide. These can be logical checks, physical checks, name checks, inherited, signal type, and constraints. Net highlighting is a very useful feature that you can use. You can go to the View menu and choose Net Highlighting to highlight all the instances associated with a net. When you move your mouse cursor over a net, the chosen net and associated net paths get highlighted. The net name is displayed in the status bar. You can also enable the dynamic net highlighting through the Display Options form accessed by going to Options and choosing Display and turning on the Dynamic Net Highlighting button. You can also highlight bus bits. Hovering over any part of the bus or the bus will highlight related parts in a slightly different color. The names of the associated objects on the selected net also will be displayed on the status bar. Let's move our focus now on how to start the Spectre Classic simulator and perform a quick netlisting operation from the schematic editor. You need to first initialize Spectre, and to do that, you need to add the Spectre menu to the schematic editor environment from the available plugins. Go to Launch, choose Plugins, Simulation, and then choose Spectre. You will see that Spectre gets enabled in that menu. This will add the Spectre menu and its associated options to the schematic editor menu bar in the cockpit. You need to first initialize the Spectre environment, and to do this you can choose Spectre Initialize. This brings up the Initialize environment form that you see here. You can enter the name of the simulation run directory and click OK. All the other options in the Spectre menu that were not accessible earlier are now enabled, and you can choose Spectre Netlist Simulate to open the Netlist and Simulate form. You can enable the run actions here. You can choose to netlist, create or run file and simulate. Your simulation run directory is already specified, and you just need to specify the library, cell and view name. Also, you can verify that Spectre is the simulator that is being used, and you can then click OK to begin your run action. Once netlisting completes, you can view or edit your netlist file in multiple ways. One of the ways you can do that is by using the Edit Netlist File option accessible by going to the Stimulus option in the Spectre menu. This opens your netlist file in an editable format in your chosen editor.